Hello everyone and welcome to this webinar. My name is Michael Evangelista and I will be your moderator for today. Just a few reminders that you are in listen. However, you can type in your questions anytime by the end of this presentation. By the way, the recording and certificate will be sent out in 2 days time for this webinar. Our topic for today is about why to test a motor, and it will be presented by Paul Knapp, the Global Sales Manager for Megger Baker Instruments. So without any further ado, let me hand you over to Paul. Paul?
Thank you, Michael. And thank you everybody for attending this webinar. This webinar is going to be in really two parts. The first part today is just discussing really why we should test electric motors. There are various maintenance strategies in the field where some people use use electrical testing to look at the condition of their electric motors, and others run to fail, and several different strategies in between. So what we're going to look at is why do we test electric motors to start with. Megger has a instrument range that is designed specifically for testing electric motors. We test motors while they're in operation, and we also test motors while they're static, offline. And this enables us to trend results and do comparison testing to look at the deterioration of the motor over a period of time. There are lots of instruments on the market that can do this, and lots of different tests that can identify different aspects. A lot of them are generic. They're also electrical tests for looking at other electrical machinery, wiring, etc., panels and so on. But the type of equipment that we're talking about today is designed specifically to look at areas where electric motors will fail and aspects of that deterioration of the insulation and the condition of the motor internally to identify where issues start in their root cause condition. So my name's, first of all, I'm going to run through a little bit of information about myself. I'll turn the camera off now. I think you've probably seen enough of me already. So let me move on to the presentation. So why do we test electric motors? Well, first of all, like I said, a little bit about myself. I've worked with electric motors all my working life. I've been testing them since I was a young man. I'm not so young now, but basically I've had 30 years experience of testing motors in the field, in a workshop environment, condition monitoring those motors, physically taking them out of situ, repairing them, reinstalling them, and getting them back up and running and commissioning them. So electric motors has always been in my knowledge base, and moving forward we're going to start expanding with Megger into lots more avenues of condition monitoring and rotating plant maintenance equipment. When I say we're part of an organization called Baker Instruments that joined Megger a couple of years ago now, and we're starting to expand and get more involved with the Megger organization to reach our customers globally. So as you can see by my list of information there, I've had the good fortune to work in the UK, in the US, in Asia, in many countries in Asia, and I now live in Australia. This has all given me great experience and a good knowledge across lots of different segments of industry, and seeing the different applications that motors operate in. So that's enough about me. First of all, we're going to talk about electric motors then. So what do they drive? If you actually think about an electric motor, it drives literally everything that rotates. Of course, we've got engines and other quite obscure drive mechanisms, but really electric motors keeps industry running. You know, they drive pumps, fans, belt drives, compressors, mixers, blowers, gearboxes, trains, cars, forklifts, hoists, cranes, grinders, conveyors. And that's just some of the examples that I've listed there. You can see that, that a lot of different industries in the market will have pumps, for example. A lot of them may not have pumps. Maybe they've got belt drives. Maybe it's a mine site and conveyors. Maybe, some food and beverage customers will have more mixers and, gearbox drives and things like that. But each of the industries and the segments are driven by an electric motor, and the electric motor has the same components internally. They're not different. Yes, the gearbox on a food and beverage drive system might be very different to a mine site, but the fact is that the electric motor side of it is very universal. So we apply the same globally accepted tests to identify areas of deterioration within the electric motor. But as you can see from this list, I mean, this covers literally everything that rotates. And I'm going to just run through some pictures to give you an idea of just how prevalent they are in industry today. So there are 3 points when it comes to motors which makes them very important. First of all, unscheduled electric motor breakdown is one of the most costly issues maintenance teams face. Yes, we can do vibration analysis, we can do electrical motor testing, we can do thermography, all giving us different ideas of how we can reduce the breakdown and give us preempt warning before a breakdown occurs. This enables us to plan ahead, avoid the costs that are associated with downtime, which there have been many studies, but usually 8 times the cost of a scheduled breakdown, a scheduled, shall we say, outage, compared to a breakdown in the field unexpectedly. 8 times the cost, so that's huge. That's mobilization of people, and that can vary massively as well, because what happens if a motor breaks down unexpectedly and they don't have a spare unit? Then we've got to try and locate one. What's an unusual frame motor? And so on and so on. So it's very important that we try to, in high volume manufacturing processes in particular, it's very important that we are able to identify weak points and cut these problems out before they occur. Electric motors are the most common rotating plant in industry. As you've seen, the list is quite long of what electric motors drive. So electric motors are should be a big concern to any electrical maintenance team or any maintenance team full stop, because they're so common across their plant. They're so expensive, and if they break down unexpectedly, they're aware of the issues that they concern. So, there's 2 reasons there already. One, it's the biggest cause of unscheduled breakdowns, and 2, it's the most common element within plant today. 3, they're the biggest energy users. Energy is much more important to customers and to industry today than it ever has been in the past. We're working under stricter monetary guidelines these days. Everything has to be scheduled to be its most efficient. And when we look at the costs associated with electricity, the prices have been increasing over the years, and probably the biggest bill that a business will face these days is energy. So electric motors are the biggest user of this energy. When we look on average for industrial facilities, and it does vary quite a lot, but 65% on average of all energy used in an industrial environment goes through an electric motor. So if you look at these three areas, and you can see that electric motors are very, very important to industry. They're very important to a particular plant to make sure that they're doing their most to keep them running. They're doing their best to avoid these breakdowns. They've got spares and they've got backup plans. They're doing as much testing as they can in an efficient way that would give them the opportunity to avoid said breakdowns, and also to make sure they're running economically. The energy that they're using isn't being wasted. It's actually going to be used through the motor efficiently and to its full potential. So these are three reasons why electric motors are very very important and considered to be extremely like I said, important to people in the field. We have to be able to identify any of the issues that can happen through electric motors. And it might not even be the electric motor itself. It could be the load. It could be the power supply. All would lead to the electric motor failing. So we have to incorporate all of these different strategies and tests to be able to confidently say that we've done as much as we can to avoid electric motor failure. So this is what happens, and this is an example of an electric motor that's failed. You can see that the end cover has been pulled off the electric motor, but the rotor has been so hot inside that it's actually melted. So this motor is now scrap. There's nothing we can do with that motor. The repair shop, the supplier, it is very extremely rare, if not very close to impossible in many ways, to efficiently replace that rotor. So in other words, we have to replace the whole motor. The rewinder or the repairer can't even just repair the windings because the rotor is at a point where it is scrap. It's just no use anymore. So, and this occurred just because the insulation between the turns and the coils started to break down, created a short, the phases become imbalanced, the heat became hotter and hotter inside until it reached this point. All of this can be eradicated by regular testing, but we have to apply the right tests, and this is where it also becomes important and practical. Because there are so many tests on the market, what tests do we use? Insulation resistance is a very common test used for all sorts of general electric procedures. Even if this motor would have had the best results for insulation resistance, it was 500 megohms to ground, yet it could have still failed within a few minutes from doing that test, simply because we weren't applying the correct test to look at the condition of the winding. Same as if we were doing a resistance test. 5 minutes before this failure, we could have done a resistance test across the phases, and the phases would have been perfectly balanced, and yet the motor still failed. So we've got to apply the right tests to be able to functionally be able to offer our plant manager, our reliability of the equipment that we're testing and the maintenance plans that we have for it. So let's look a little bit deeper at some of these, who should be concerned and where these applications are. So let's just look at this one picture in a rolling mill. I don't know if you can see, but I can see probably close to 150 large electric motors in this picture. And this is just one line. That's without all the fans, the pumps and things which are subsidiary around this main component of that business. So electric motors, any one of those fail could lead to that whole line stopping. So the cost would be huge to the client. Paper mill. As you can see, there's a couple of paper mills there on a roller. Now, for those of you that don't work in paper mills, a paper mill machine could be 100 meters long, maybe 150 meters long, with literally hundreds of these rollers. So any one of these motors stop, the whole machine stops. So having that kind of reliability and doing as much as we can to test these electric motors effectively is also very, very important to that business. Mining. Here you can see some large motors on a conveyor. You can imagine that if these motors stopped, then the whole business would stop. They wouldn't be able to load the rail trucks, etc., etc. Food and beverage here, but this could actually be the basement of any tall building. A tall building, for example, in a city is absolutely full of pumps. And again, if we haven't got the if we aren't doing tests and we haven't got redundancy in what they have, which is becoming rarer and rarer. And what I mean by redundancy, I mean that there's a spare unit. There's they can quickly switch from 1 to 2. You know, designers are reluctant to do that because everything cost is trying to be cut everywhere. Even keeping spares anymore is a lot of customers are not keeping spares on the shelves like they used to. So therefore they have to have also take into consideration in a breakdown environment, where are they going to get the unit from? How critical is it? And how long will it take me to do that? Trains. This is a DC motor that drives trains. We've all got, you know, if one of these breaks down in the field, the train stops. So again, it's critical. I'll go through these a bit quicker now. Shipping. A ship is full of pumps and gearboxes that need to run. I mean, the one on the left there, the blue one, is a bow thrust, and if the bow thrust stops, that means they can't. The bow thrust drives the ship up against the quay and helps maneuver it. If they don't, on a bigger ship, they might have to get a tug in to push them up against the dock instead of using their own power. That is extremely expensive and can cost $30,000-$40,000 to hire a tug. So yeah, having a failure for something as simple as that could really be costly in the shipping environment. Power stations. If a power station was to drop out of the grid, we wouldn't notice it because usually there's a backup grid system that if anything did happen, there's always more power in the grid, and that's the design. However, that particular power station, because it's dropped out, would probably get fined. It would probably it would lose a lot of money, put it this way. So once again, electric motors are very important that we don't have failures in a power station, especially on the critical plant. Oil and gas, similar thing. Electric motors in the oil and gas field have flame paths and are very expensive to buy and to manufacture and to repair, because once an electric motor has been dismantled, every single path, and what I mean by path is every single spigot or metal to metal contact from, say, the terminal box to the frame of the motor has to be measured, because it's the flatness and the length of the flatness that puts any fire out. So if there was a spark inside of the motor, it couldn't get out of the frame because of the flatness of the flame path, and the fly would be extinguished as it was trying to escape. So again, electric motor testing in this environment is also extremely important. Now, because it's in a hazardous area, we might not be able to go to the actual terminal box itself to do the tests because of the environment. However, as you'll see shortly, the tests that we should be doing are probably not at the motor itself when it comes to the electrical component. It should be from the MCC, and we'll talk about that more in a moment. So, crushers in the mining environment, very, very large motors, have a terrible life. They're always have been in a very aggressive dirt. Contamination is a big problem, and again, they can fail without notice and be a big stopper the industry and the flow of materials. So this is something that is very important that we test as well. Plastics factories, and now I'll just skip through them. Lift motor drives, blower units, and pumping facilities for utilities. Compressors are often driven by electric motors. So if there's any compressed air or gas that needs in the plant, they're driven by electric motors. Electric motors that drive conveyors. Also, we're talking huge costs. If this breaks down, the ship doesn't get loaded. And you know, for a ship to be at the dock and not be loaded is incredibly expensive. And the fees, the penalties that go with this can be horrendous. Safety for fire pumps, cranes, fans, gearbox drives, pumps in the field, you know, submersible pumps. The pumps are absolutely everywhere. Even spares. We're looking at here at a spare rack that's been in a facility probably for quite some time, some of these motors. How do we know the condition of these motors? If we have a failure in the plant and we come out and we replace that, often if these motors have not been stored correctly, tested regularly, then you know, we might be putting a bad motor into a place of a failed motor. So it's also very important that electric motors are tested on a regular basis, and this is often forgotten. And more often than not, and I've got many case studies that I could share with you of motors failing straight after another motor has failed, simply for the fact that the condition of the motor that they thought was a new motor or had been repaired in the past, had just been on the shelf for too long, and the bearings had become brunelled, and maybe even moisture had been sitting in there, etc., etc. So what can we do? Well, field maintenance and predictive maintenance is a very important part of this strategy to enable us to identify failure mechanisms within electric motors. There are several ways we can do this. We can look at the mechanical aspect, we can look at the power quality aspect going into the motor, we can look at the performance of the motor itself, and of course the load. And for an example, let's just say we have a slipping belt on an electric motor, and the belt that was slipping, if you can imagine the electric motor as it's in operation, every time it slips, the current is going up and down. And if you can compare that to driving a car, you're basically driving the car, dabbing your foot on the accelerator. Now, sooner or later, that motor is going to fail, just like your car would if you kept dabbing your foot non-stop on the accelerator. So sometimes in a noisy environment and guards covering a belt, we can't see this. So we need to have the right test to be able to identify that. And that can be done very, very easily just by monitoring the torque of an electric motor from the MCC. So without going too much into depth on individual tests, but there are several that we can apply quickly, easily, and come up with the right answers as to the longevity, likelihood of that electric motor. Here's an example of how practical it can be. That is actually me at a large steel mill in Australia. As you can see there, there's about 7 or 8 panels in a row. It's very difficult to get to the motor and test it itself. If you can imagine the electric motor there is under a cover, how long would it take for a maintenance team to pull the cover off and be able to take the guard off, test the windings, put the cover back on and get it up and running again? And that is if the motor next to it isn't running, because you can see there's a shaft next to it. So health and safety may not enable us to be able to even do those testing. So what do we do? Just leave it? Do we run to fail? No. What we need to do is to then run some tests from the panel to help us identify. Okay, we've run 10 motors in a row there that you can see the panels open, and we've been able to say number 1, 2, and 3, and 4 is good, and say number 5 has got an issue. 6, 7, 8, and 9 and 10, are all okay as well. So now that maintenance team, with the information that we've got, can plan a suitable shutdown to avoid the costly downtime unexpectedly, and look at the motor, take the cover off, investigate what strange results that we found. So this is the idea of predictive maintenance. This is the idea of of why we test electric motors in the field, is to basically help us identify areas of where an electric motor can fail. Now, electrical testing isn't going to give us an idea of a bearing failing. So we have to combine different technologies to come up with the right answers. And this is something I hear a lot when we talk to clients. How can we justify doing all these different tests to an electric motor? Well, yes, you could do thermography on the panel. It's going to look for loose connections, basically. Can we do grease analysis? Yes, you can. Usually if the motor is big enough, or oil analysis. Can we do vibration testing? Of course you can, if you can get access to the motor. Can we do electrical testing? Okay, so already you can see that we've got a list of 5 or 6 different ways that we can test electric motors to identify different failure mechanisms of an electric motor. So again, I ain't going to go into too much depth on this today, but next week when we look at it, we're going to be looking at all of the different failure mechanisms of electric motor and what tests could be done to identify that and what test equipment could be used. And the reason why this makes it more practical for customers and clients is that they don't have a huge inventory of different test equipment or theories of how to test the electric motor. You know, we're looking at the areas where electric motors fail 90% to 95% of the time, and we're hitting them with the equipment that will identify those issues quickly, easily, and not in a way that's going to be too taxing on our resources. So I hope that gives you an idea of the type of motors that we have in the field. This slide is another example. I can run you through all these. The top one on the left there is at a steel mill in Australia. The middle picture is a Suzuki factory in Mumbai. On the right, this is a aggregate plant in Australia, but in Sydney, I believe. The bottom left is a power station in Kuala Lumpur in Malaysia, and the one on the right there is a scrap yard with a huge motor that chops up, basically just saws through whatever metal that's going through scrap and chops it up into small chunks. Massive motor, very little maintenance was done, and if this failed, the cost of this repair would be huge, and they basically didn't have a spare unit for it. So and that became an issue when we found a huge problem with that motor. So as you can see, there are different instruments in the picture there. The one on the top left and the top right is an instrument there where we're actually testing the insulation between the windings and the turns. The top one in the middle there is a picture of an instrument that's looking at the performance of the electric motor. And by looking at the performance from the panel, we can see the torque of the load. So we're also enabled to actually measure bearing condition through the panel and through the torque. Just like vibration analysis, we're able to identify fault frequencies in the torque, just like we can with vibration. So it is another aspect of our testers that can give really good results unexpectedly, as well as look for hot connection joints in contactors that are starting to burn out, as well as just looking at the more basic performance of the electric motor itself, the efficiency, the rotor bar condition, etc., etc. So I hope that has given you some good information. Sorry, this was just a follow-up. When it comes to testing, information is all important. The tester himself needs to know whether the unit is acceptable, whether it's pass-fail. And one of the good things about a lot of condition monitoring equipment is being able to run simple, acceptable traffic light style alarm system. Here you can see that we have a red for danger or critical, and we have a warning for yellow and green for pass and acceptable. So there are lots of different tests that we can do, like I said, but we want to make it efficient. So we need to know what each of these tests are really going to identify and what benefits they have to the system as a whole. So as you can see, just to run through this single one, you can see that the insulation resistance to ground was acceptable. The resistance between the phases was perfectly balanced, also very acceptable. The ground insulation, when we did a high voltage test, so we tested the voltage at the running operating voltage, and everything was fine to ground. We increased it to look for a weakness at a higher level, trying to create a little bit of predictive maintenance here by looking ahead, by increasing the voltage to the type of voltages that a motor will see during its startup and stopping process. And then finally, a test that will identify the weakness between the coils and the turns and the insulation breakdown over time. And all of these results are trendable. So we could go back to it and we can look at graphs, look at deterioration. So there are some really good tests here that can help us plan a good strategy, be confident that we're monitoring our plant in a way that's going to give us true results and not unexpected breakdowns. So that's the end of the of that particular presentation. What I would like to do now is just really give you run a video. Now this video is just an overview of some of the electrical test equipment that we have and what the strategy is behind that, and hopefully it will help you identify similar issues with plants that you work in or that you know, or customers that you have that also you think might benefit from this type of monitoring. So I'm just going to get the video running right now. Hopefully this works. Okay.
Electric motors are everywhere in industry. When these motors fail, the costs of downtime are very high. Lost production, lost profit, and loss of confidence if the failures were unforeseen. Many sites use vibration monitoring on their motors. This is good, but vibration monitoring misses up to 50% of motor failures. These failures are due to insulation failure and motor operating point problems. Let's look at each. AC induction motors make up the majority of electrical motors and are covered here. DC, synchronous, and other motor types will not be covered in this video. Industrial AC induction motors use magnetic fields to cause the shaft rotation. Magnetic fields are created by electric currents. The AC power source provides the currents that flow in the motor. The stationary part of the motor, the stator, is made of several wire loops which are physically aligned to create strong magnetic fields. Due to the AC nature of the power source, the magnetic field direction rotates in the center of the stator. In the center of the stator is the rotor, the part of the motor which is connected to the shaft and rotates. The rotor has no electrical connections to the stator or the power source. Rather, the magnetic fields of the stator induce currents to flow in the rotor. These
I'm sorry everybody, I'm not sure why, but the video is playing on my PC, but I've been told that that the video is not playing for you in the field. So I'm just going to close it and then play it again. Try that again. Sorry about this.
Electric motors are everywhere in industry. When these motors fail, the costs of downtime are very high. Lost production, lost profit, and loss of confidence if the failures were unforeseen. Many sites use vibration monitoring on their motors. This is good, but vibration monitoring misses up to 50% of motor failures. These failures are due to insulation failure and motor operating point problems. Let's look at each. AC induction motors make up the majority of electrical motors and are covered here. DC, synchronous, and other motor types will not be covered in this video. Industrial AC induction motors use magnetic fields to cause the shaft rotation. Magnetic fields are created by electric currents. The AC power source provides the currents that flow in the motor. The stationary part of the motor, the stator, is made of several wire loops which are physically aligned to create strong magnetic fields. Due to the AC nature of the power source, the magnetic field direction rotates in the center of the stator. In the center of the stator is the rotor, the part of the motor which is connected to the shaft and rotates. The rotor has no electrical connections to the stator or the power source. Rather, the magnetic fields of the stator induce currents to flow in the rotor. These rotor currents create a magnetic field which interacts with the stator magnetic field to create the shaft rotation. The stator insulation is most prone to failure. Insulation strength degrades over time due to heat, electrical stress, mechanical stress, abrasion, and contamination. The most common insulation failure is between turns of wire that are next to each other in the same coil. This is called a turn-to-turn fault. When this fault occurs, the motor will draw a lot of current, quickly overheat, and can melt down in minutes. The surge test can reliably find the strength of turn-to-turn insulation, giving you early warning about when the insulation is weak. When the insulation fails, and there is a path to the core, it is called a ground wall insulation failure since the stator core is at electrical ground. Oftentimes, when a motor overheats or has a turn-to-turn failure, the excessive heat will cause a ground wall insulation failure also. Ground wall insulation strength is measured with the Megger test at low voltage, but this test misses many ground wall insulation failures. A better test is the DC high pot and step test, which measures insulation strength at higher voltages. Stator insulation faults are responsible for about 30 to 40% of motor failures. One of the major causes of insulation degradation is heat. To understand more about what causes excess heat in the motor, let's look at the entire power, motor, load system. Electric machines are designed for good incoming power conditions. When power conditions deteriorate, excessive currents can flow in the machine, generating excess heat and shortening machine life. Incoming power tests look at voltage and current levels, distortion, and balance. Electric motors are designed for specific conditions found on the nameplate for the motor. This includes things such as voltage and current, but more importantly, motor speed, torque, and load ratings. Running a motor in an overloaded condition can quickly reduce the motor lifetime. The machine load is what provides the benefit of the machine: moving air, compressing air, moving rock, pumping liquids, moving a vehicle, processing pulp, etc. Ideally, these loads do not overload the motor, even temporarily. By measuring electric motor torque, the machine load can be examined in real time. Megger Baker Instruments' electric motor condition monitoring solutions completely address the faults not covered by vibration monitoring. Baker static motor testers completely assess the insulation system of the motor. These tests are run when the motor is off, disconnected from the AC power source. The most common insulation failure is between turns of wire that are next to each other in the same coil. This is called a turn-to-turn fault. The surge test is the only test that can reliably test turn-to-turn insulation. The surge test also finds phase-to-phase and coil-to-coil faults in the stator windings. Ground wall testing is done with a Megger test, but Megger test alone is an incomplete test of ground wall insulation. To completely test the ground wall insulation, high voltage step, ramp, and high pot tests are also used. Baker Instruments static motor tests are non-destructive and follow IEEE and IEC motor testing standards for motor insulation testing. Additional tests available include resistance, inductance, and capacitance for verification of motor winding construction. Now, let's look at the motor operating point using Baker Dynamic Motor Analyzers. The operating point is measured while the motor or machine is energized and operated. Connections are made to measure the motor voltages and currents. Electric machines are designed for good incoming power conditions. When power conditions deteriorate, excessive currents can flow in the machine, generating excess heat and shortening machine lifetime. The EXP4000 and NET-EP analyze incoming power, including voltage and current levels, distortion, and balance. The motor performance itself is analyzed using motor speed, torque, and load ratings. Motor efficiency is also presented. Running a motor in an overloaded condition can quickly reduce the motor lifetime. The load performance is analyzed by looking at the motor torque output. The output torque required is determined by the load. Baker Instruments Dynamic Motor Analyzers allow you to look at the load torque in real time to find even temporary overload conditions or machine faults such as cavitation or unbalanced loads. All operating point measurements can be done on line-driven and VFD-driven machines. Monitor your entire machine systems with Megger Baker Instruments electric motor condition monitoring solutions. Doing so will help give you early warning of failures and allow you to take action to extend machine life. For more information about Megger Baker Instruments electric motor test equipment, go to megger.com/Baker.